Hello. The majority of the people listening to this are going to be Miss Sherwood's class. Yo, it's Mr. Skis again. How's it going? If you're one of my kids going back and listening to this, great, terrific. I mean, you had me in class for this lesson. However, you might feel the need to go back and watch this video. Good for you. But yo, Miss Sherwood, kids, what's going on? So, last lesson, I'm literally recording this right after recording the last one. So you listened to the lesson one the other day, a couple days ago. Now we're doing lesson two. Last time was and, or, and conditional stuff, and the two-way tables. So keep all of those things in mind. You might find it's a little too difficult for me to flip pages to show you those examples again. Actually, I have the document right here. I could show you the examples. Okay, I might do that. Anyway, sorry. So let's jump right into it. Today we're dealing with independence. So to be independent, to be separate, that something doesn't affect you, right? When you think, oh, you're independent, I can do my own thing, right? There's nothing standing in my way. Well, independent with events, meaning, oh, if one event occurs, it doesn't affect the other, is what independence means. And a common misconception is that, like, the two events are what we call disjoint or mutually exclusive. Independence does not mean disjoint, meaning like, oh, they're two completely separate things. Disjoint refers to things that have literally no elements in common, like black versus red cards, right? They share nothing. So if something happens to black, well, then it doesn't matter. It has no effect on the red, right? That's not what independent means. Independent means when one event occurs, it has no effect on the other. And something that happens to the red cards might be reset, and then the red cards are still fine. Let's look at the examples. I'm going to skip these little blurbs here about independent and dependent real quick. Let's just look at the difference between them. Independent versus dependent. Independent events have no effects on each other. Dependent events, well, they do have an effect. Independent events, they don't change one another's probability. Dependent events, that first event is going to change the probability of the second one. And oftentimes things are replaced in independent events. Like if I have a bag of marbles or a deck of cards, if I put a card back, literally it's the same deck of cards. If I don't put that card back, oh, wait a minute, I don't have 52 cards anymore. I have 51. The probability is now different, right? I'm not drawing out of 52 cards. I'm drawing out of 51. So let's look at these events. Rolling a 6 on one die, and then you roll a 6 on a second die. Does the result of die 1 affect the result of die 2? No. I really hope you're saying no. They're independent of one another. It doesn't matter what happens on one die, right? I don't know if you've seen any craps being played. That's a game that involves a lot of dice. You probably haven't seen craps. Maybe you have. But the point is it doesn't matter what's happening at a craps game at one table versus another. It doesn't matter if one die rolls a 6 and another does, and they're not going to affect each other. Two complete separate dies. Picking and winning a horse in the first race, picking and winning a horse in the second race. Well, it doesn't matter the results of one race, right? I mean, psychologically, it might matter, but when it comes down to the probability, which is straight up math, it's the same horse. It's just a different race. It doesn't matter what happened in the first race. It's a new race. They're starting at the starting line. It's been completely reset. Independent. Drawing an ace, placing it back in the deck, and then drawing another ace. Well, if you're drawing an ace and then you put it right back, you've completely reset the situation. They're independent. It doesn't matter if you drew the ace that first time. You put it back in, oh, it's the exact same deck. Nothing's changed. If you draw a king, you don't put it back in the deck. Okay, so this is what I was saying, 52 versus 51. I have 52 cards. I draw an ace. Oh, sweet. I don't put it back, and I try to go for a queen. I am drawing out of 51 cards. The probability of drawing a queen has now changed. It's now 4 out of 51. So we say it's dependent because it changed. If it's not replacing, it's dependent. So both of those. Flipping heads on a coin, rolling 5 on a dice. Really hope you're saying independent there. They have nothing to do with one another. Spinning an 8. What the? Why do I have? Okay, I don't know how I just did that. Spinning a 8 on the color spinner and flipping a coin. What does a spinner have to do with a coin? They're independent. Picking a student to present their project, picking a second student to present. Well, if that person has already presented, they're not going to present again. They are no longer in the group of students to be chosen. So if there are 40 kids in your English class and you're presenting some sort of a report or a presentation about a book or something, well, when person A goes, they're out. So now there's only 39 left to choose from. So the probability has changed. All right, so let's go back and look up at the nitty-gritty here. Two events are independent if the outcome of one event does not change the probability of the second. That's what we just said. In other words, this is true. What does this mean again? Probability of A given B. So if I tell you that event B happened, it shouldn't affect A, which is why it stays the probability of A. It doesn't change, right? So let's flip back. We had this for conditional probability. We had this thing. We had to do and over, right? And hopefully you remember that. Well, you don't have to do that if the events are independent, because whether I give you event B or not, it doesn't matter because they're independent. It doesn't matter if something happened first. So whether I gave you this or gave you that, who cares? They're independent. Also, fun fact, this is true as well. A times B is equal to the probability of A and B. So dependent, that is not true, right? If I give you B, then it does have an effect on A. And it doesn't just stay its regular probability, right? This equation up here is saying, if I give you B, nothing happens to A. It's just good old probability of A. But if I give you B for a dependent event, wait a minute, something different happens. So these problems can be really easy because of independence versus dependence. So the probability that Jordan wears his AirPods to school is 0.95. The probability he wears his LaFleurs to school is 0.55. The probabilities of these two events are independent. What is the probability Jordan wears LaFleurs given he wears his AirPods? It doesn't matter he wore his AirPods. Who cares that he wore... Oh my gosh. I need a freaking new stylus. I'm starting over. Who cares that he wore AirPods? I don't care. They're independent. The probability of him wearing LaFleurs stays constant. It doesn't matter whether he wore AirPods, whether he wore some new Bose wireless earbuds. It doesn't matter whether he wears some classic Sony Walkman headphones. It doesn't matter. Who cares? The events are independent. If the events are independent, the probability stays the same. So what's the probability he wears LaFleurs if he wears AirPods? 0.55. It doesn't change. In Chicago, the probability of a bus departing on time and train arriving on time are independent. So who cares whether one thing or another happens? It doesn't matter because it stays constant. The train arrives on time 60% of the time. The bus leaves on time 35% of the time. What is the probability on Tuesday that the bus leaves on time? So we want to know what's the probability the bus leaves on time given the train did not arrive on time? Who cares the train didn't show up on time? That bus is leaving on time. 35%. That is the probability. 0.35. Now consider the following. What is the probability the train is on time and the bus is on time? Oh, wait a minute. This guy here, lovely. This means and. Remember that? That symbol means and. So we're going to use this. Because the events are independent, the probability of the one event times the probability of the other event gives me and. That's a unique thing for independent events. So probability of bus times probability of train is equal to probability of bus and train. So what is the probability that the bus and the train are on time? Well, that's what is bus? Bus is, 0.35 times 0.6 is equal to, calculator, my phone is charging, let me grab it real quick. Calculator, where are you? 0.35 times 0.6 is 0.21. Boom. That is it's a little subtle thing, and you're just gonna have to know that sometimes that's gonna come into play for independent events. Oh, wait a minute, that's true. These are the two big things you want to remember for independent events. All right. So we use, moving a little bit here, we use those I'm spacing the word. We use those formulas, for lack of a better word, here they are again, to help prove independence, to help show that two events are independent. I kind of left off a sentence here when I typed this. An airport employee collects data on 180 random flights that arrive at the airport. The data is shown below. Determine if they are independent. Okay. So we are going to look at this data, this two-way table, and determine if the flights are independent. Okay. So we have domestic and international flights that are arriving late and on time. Does it matter whether one flight comes in late for the takeoff of the next one, right? Because sometimes it does, right? Like you're taking up space at the terminal, or you're going to literally use that plane to then go on the next flight. But maybe because they're international and domestic, they're completely separate, right? Maybe they're at different hangars or whatever, and it doesn't even matter. So we are trying to determine, are they independent or not? So method one is, if you can show that the probability of A times B is equal to the probability of A and B, well, then they must be independent. So what is the probability of A times the probability of B? What are A and B? Here we are over here. Let A be the event that a flight arrives late. So what is the probability that a flight arrives late? 18 out of 180. Times, what is the probability, let event B be the event that a flight is an international flight? Well, international flights, there are 60 out of 180. I probably should have put some more space on here when I typed this. So I'm going to work down. So this is all its own work here. So 18 over 180 reduces to 1/10. Please reduce to make these numbers nicer. And 60 over 180 reduces to 1/3. So we get 1/30th. So is the probability of, this is a big boy typo here. This should be and. Is the probability of A and B also 1/30th? Because if it is, then they are independent. Let's see. A and B. So that means what is the probability that is an international flight that arrives late? International and arrives late. 6 out of the 180, which is 1/30th. So because this is equal to this, that is method 1, they are independent. But let's show it the other way, because sometimes it's easier to use one method over another. We are given all of the information our heart could desire, right? But sometimes you're not given all of the blocks, right? Sometimes you're not given all of the info, and one will be nicer than the other. So we're going to use both here just for practice. So what's the probability of A given B? So given it's an international flight, what is the probability it's late? 6 out of 60 or 1/10. Because I'm not doing any multiplication and whatnot, I tend to like this method better. It also makes more sense to me, right? If B happens, oh, who cares? It should be the same as A. So what's the probability that it's late? 18 out of 180, which is 1/10. Oh, they're the same, independent. Both methods are equal. Therefore, independent. Boom. Let's do it again. Literally, I'm just following those equations. I'm not trying to reinvent the wheel here. All right, method 1 is A times B should be the same as A and B. So what are our events? Determine if choosing a senior and choosing a boy are independent. So A is choosing a senior and B is choosing, well, a boy. So what's the probability of choosing a senior? Probability of choosing a senior is, where are the seniors? Total number of seniors are 11 out of 20. What's the probability of choosing a boy? There are 12 boys out of the 20, which comes out to be, these are both divisible by 4, by the way, so that's 3/5. So 33 100ths. Now, is that the same as probability of senior and boy? Is it? Senior and boy is 8/20ths, which are both divisible by 4, 2/5. 2/5 is not equal to 33 100ths. Therefore, dependent. Let's show the other one for fun. Is the probability of senior given boy the same as probability of senior? Question mark. So given a boy, that's 12. 8 of them are seniors. Probability of senior is 8 out of 20. Whoops, those aren't equal. So dependent. You just got to use those facts, right? I mean, again, this comes back to the two-way tables. If you don't know how to read the two-way tables, well, this problem seems hard. If you know how to read the two-way tables, we're just doing more of the same, dude. Like, we're literally just doing more of the same of what we were doing last time. Like, it's really no different, right? You just need to, these things, you just need to be able to read. Probability of A times probability of B. You just need to know how to read those off the table. That's it. All right, we're almost done. Super quick. In In a certain factory, 0.64 of the employees are men. If happiness and gender are independent, and 54% of the employees are men who are happy with the working conditions, what percent are women who are also happy? If you're like me, when I read that for the very first time, I was like, what? What did that even say? So I was like, let's make a table. I'm either a man or woman, and I'm either happy or not happy. That's it. That's what it comes down to. Okay? And once I have a table in front of me, it's going to be just that much easier to contemplate, you know? And recall, so I'm actually going back to our notes for the first time from last time. Recall this situation where I was like, sometimes two-way tables do not literally need to have the number of people, the actual like count, like we had for our Marvel and DC where we like counted the number of students. Literally, you can have a two-way table that's just probability numbers, right? And that they ought to total up to 1. It's all the same, right? We just have the probability already, right? And we don't have the number of people. Who cares? We don't really care about the literal number of people. What we care about is the probability. So we already are handed some of the numbers. So our total is 1, and this is men, women, happy, not happy. So 0.64 are men, which means 0.36 are women. If happiness and gender are independent, and if 54% of the employees are men who are happy. What is that saying? 54% are men who are happy. That's telling us the and. That's telling us men and happy. So 0.54, which means there are 0.1 men who are not happy. What percent are women who are also happy? So we want this one right here. This is a hard question, I think, because it's hard. Well, the math in the end is not hard. What's hard is like, wait a minute, how do I get that number? Because I don't know how many total people are happy. So this number could be anything, right? Well, it can't be anything, right? It can't be bigger than 0.36. Are all women happy? Is this number 0.36? Probably not. How do I figure out what that is? Well, the key ingredient is that we said it's independent. So what are we trying to figure out? We want to know probability. What is happening? Probability. Why is that like selected like that? Unselect. There we go. We want to know the probability of women that are happy. So women and happy. And if they're independent, what does that equal to? Probability of women times the probability of happy. Right? You with me? Because they're independent. So scrolling back up, right? Event A times event A times event B is the same as A and B. Oh no. Whew, it scared me for a second. So we need probability of women times probability of happy. Well, crap, I don't know how many people are happy. Right? I know how many people are women, 0.36, but I don't know how many people are happy. But wait a minute, we know man and happy. So I'm going to go over here to the left now. Probability of man and happy is equal to probability of man. Oops, I need a P first. Probability of man times probability of happy. So here we go. Are you ready for this? What's the probability of man and happy? 0.54. What's the probability of being a man? 0.64. What's the probability of being happy? I don't know. So let's solve for it. Divide 0.64 away, and I get probability of happy. 0.54 divided by 0.64 is something. I don't know. 0.54 divided by 0.64 is, let's call it 0.84. So 0.84 are happy. Sweet, we now have that number. Well, if I have that number, I almost don't even need to do this calculation over here, right? I just needed that number. And now that I have that number, oh, that's 0.3. Easy. So like, it was like difficult at first to like, how do I find it? But it was like, okay, I just need to know this number, right? That's what it boiled down to. And maybe I should have said that before I started solving. I should have said, if I can get this number, well, then this number is going to be easy, right? I should have said that at the start. If we can solve for this number, then this number is easy to calculate. 0.84 minus 0.54, 0.3. But I just needed a way of solving for that. And that was this right here. Probability of male and happy is equal to probability of male times the probability of happy. So 0.64 times happy, divide away the 0.64, and you're left with happy. So what percent are unhappy? Well, this amount here, which is 0.16, 16%. All right. A group of students are asked whether they have a calculator and whether they have AirPods. What is a reasonable answer to fill in the blank if the events are independent? What is a reasonable answer? What does that mean? Well, we need this number to be something that makes one of our methods true. Either probability of A times probability of B equals probability of A and B, or probability of A given B is equal to the probability of A. We need to make this number something so that way one of these is true. And if one of them is true, well, then it's independent. Are you with me? I need the events to be independent. If they're independent, one of these things is true. So we need to put a number there that makes it still independent. Okay? So instead of saying question mark, let's call it X. Let's get our totals. This total here would be 168 plus X. This total here would be 82 plus 38, which is, can't do math, 120. 168 plus 82 is, I did this already, 250. Okay, it's not writing correctly. 250. And then this total would be 38 plus X. We just don't know what that X is, right? So what does that make the total number of people surveyed? 288 plus X, interestingly enough, right? Okay. So we want one of those things to be true. Which one should we do? I like this one. Why? Because it doesn't involve any multiplication. That's why. So probability of A given B should be equal to the probability of A. Well, what is A and what is B here, right? That's a question. Well, it's got to involve X, yeah? We got to make it involve X somehow. So let's say the probability, I mean, I guess it doesn't really matter. I'm pretty sure it doesn't matter. You're probably like, you're pretty sure. Well, that's because I haven't done out every single possibility. But you could throw anything at me. What probability of being AirPods given no calculator, or no AirPods given no calculator, right? It could be anything. You could throw anything at me. Let's say A is, I'm going to do a different one from what I did in my own notes, which is probably a bad idea, but I'm going to do it anyway. Let's say A is calc and B is AirPods. Okay, you with me? So what we're saying is, what is the probability? So back up. The probability of owning a calculator, that's event A, should be equal to the probability of owning a calculator given you own AirPods. So let's calculate the left half first. Given you own AirPods, 250. The probability you own a calculator is 168. 168 of the 250. That should be equal to 168. Oh, no, it's not. Hold on. That should be equal to the probability of owning a calculator in general. What's the probability of owning a calculator? Well, how many people own a calculator? 168 plus x all over 288 plus x. You're probably like, what? This is true. This is another hard problem that will be on the EOC. Remember last time I was saying this type of weird hard problem is going to be on the EOC, on the final exam. A problem like this, right? Where it was kind of like different and unique. This question, similar type problem, will be on the EOC, okay? So it feels strange. You're like, man, this doesn't, am I doing this right? Yes. Trust the table, right? I'm just using the table. I chose these events at random and I'm like, all right, tell me what to do, table. Given AirPods, what's the probability on a calculator? 168 of the 250. Okay, how about just owning a calculator? Well, what's the total number of people? 288 plus X. How many people own an AirPod? 168 plus X. I'm just trusting the table. We did the table right, okay? So how do we solve this? Cross multiply. The numbers are going to get obnoxiously big because it's 168 and 288, but let's cross multiply. So 168, I'm going to zoom in. So when I cross multiply here, it's 168 times 288 plus x equals 250 times 168 plus x. I'm being super careful here because look at this. Once I have to I'm cross multiplying. I have to multiply by both of these things. I'm about to distribute, yo. I'm distributing. So 168 times 288 is, 4,384 plus 168x equals 250 times 168 is 42,000 on the nose plus 250x. Get your like terms together. So subtract this guy over to the other side and I get 250 minus 168 is 82x, and 4,834 minus 42,000 is 48,384 minus 42,000 is 6,384. Divide each side by 82. I'm running out of room. Crap. X is, divide by 82. 77.85. So what is a reasonable number that could go there? 78. All right, that's the closest number. That's a reasonable number, 78. All right, last three. Let's do these super quick. I'm ready to be done, aren't you? I've made 2 videos in a row. I've been recording videos for almost 2 hours straight now. I'm ready to be done. Not that I don't love this. Wow, I love math. No, I really do. But I'm ready to eat some food. I haven't eaten breakfast. It's almost 11 o'clock. It might as well be lunchtime. Here we go. Find the probability of the event if the cards are 1 replaced and 2 not replaced. We need to add a little something here. Probability, the probability of multiple events means multiple events in a row means we must multiply. Meaning, let's say we want the probability of 1, then 2, or how about I use A instead of 1? Probability of A, then B, then C. That is equal to the probability of A times probability of B times the probability of C. Okay? But look out for dependency or dependent events. Because if the events are independent, the probabilities are changing as we do the problem. Okay? Let's see it happen. A 10, then a 5, then a 7. If the cards are being replaced, the probability of a 10 is 4 out of 52, or 1/13th. The probability of a 5 is 4 out of 52, or 1/13th. And the probability of a 7 is 4 out of 52, or 1/15th. So probability of that, then the probability of that, then the probability of it, just to multiply the 3 together, and you get 1 over 2,197. Not very likely, right, for something so specific to happen. But what about if the cards aren't replaced? That's when it gets interesting. The probability of a 10 is 1/13th. What's the new probability of a 5? How many total cards are there now? 51. But there are still 4 5s. There are still 4 7s. But now that we've taken the 10 and the 5 out, how many cards are left? 50. So this reduces down to 2/25. So 4 times 2 is 8. 13 times 51 times 25. Plug that into a calculator, you get 16,575. Oh, I'm feeling sick. I'm so hungry right now. Oh my gosh, I'm dying. Deep breaths. All right. You with me here, though? Multiple events in a row just means multiply. That's called the, I believe the fancy pants name for that is the fundamental counting principle, I think, if I remember correctly. I don't know. Don't quote me on that. I think it's the counting principle. A king followed by another king. All right, well, there's 4 kings out of 52, so 1/13th. And you put that king back, 1/13th. 1/13th, so 1 over 169. But if you don't replace it, okay, there's 4 kings, 1 over 13, 4 out of 52. The second you take a king and don't put it back, there's only 3 left, and there's only 51 cards in the deck, which is 3 over 663. These are easy, right? These are easy. 3, if I'm not replacing, 1/13th. Queen, if I'm not replacing, 1/13th. Or, sorry, if I am replacing. Right, I'm putting it back in the deck, Then 2 jacks in a row, 1/13th, 1/13th. Why is it always 1/13th? Because there's only 4 of each card, right? So it's always going to be 13, 4 over 52. So 1/13th and 1/13th and 1/13th and 1/13th is 1 over 28,561. But the second you take cards out, 3, oh my God, I'm so hungry. 1/13th for that first card times, okay, I still have 4 queens, but there's only 51 cards in the deck. And then 2 jacks in a row. There's still the 4 jacks because I've taken a 3 and a queen. There's only 50 cards left in the deck. But 2 jacks in a row means, oh, whoops, I've taken one of the jacks, and now there's only 49 cards left. This reduces the 2/25. 3 goes into 51. That's 1/17. Can I do any more reducing? I don't think so. 4 times 2 is 8, and then 13 times 17 times 25 times 49 is a big obnoxious number. 270,725. Okay, there we go. I did it. We did it. Oh my gosh, we did it. All right, so that's the end of the unit. We're having a good review day. It's not your casual review day. I don't know how review day works in Miss Sherwood's class 100% of the time, but I typed something up that was some good hefty problems that hopefully you guys do together next time when Miss Sherwood is back. Skis folks, my kids, if you're watching this, right, thanks for watching this and appreciating it and going back and trying to maybe brush up on some things. Do your practice, do your practice, do your practice, do the Google quiz, okay? Please. This was the last lesson of the last unit. We're not doing anything new from here on out. It is review for this test, then the test, then review a couple days for the final, and then finals week. It's crazy. It's literally crazy. I don't know how it happened so quickly. It's crazy. All right. That's that. Thank you.